Now, I say this equation is very easy to solve. That really depends on the EMF of your source. If you have a constant EMF, just a plain old battery or something, close the circuit, then it becomes fairly easy. But our procedure for solving this, the first thing we need to do, and I'm just going to give you the procedure, I'm not going to talk about superposition and all the reasons this works. If you're in differential equations, you know all that. If you're not, you just need a quick and dirty way to solve this. And then after you've taken differential equations, you're ready for a more advanced course. Differential equations is not prerequisite for this course, but basic calculus is, and all you need is basic calculus in order to solve this. So, to solve it, you make the assumption that your current is some constant multiple, A is just a constant, times e to the RT. And you solve the equation without the EMF of the source. You solve the equation it would be if you didn't have a source. And the equation is just this. And this equation turns out to be extremely easy to solve. Okay? If I is this, then di dt, well, by the chain rule, you're going to get a factor of r. So di dt is going to be r times a e to the RT. So replacing di dt by r times a e to the RT, we get L times r a e to the RT. And we have IR. Well, I is a e to the RT, so we're going to have an a e to the RT multiplied by r. And now we can simply divide out the a e to the RT, and we get a very simple equation that we can solve for little r, the number that goes in the exponential. And that solution, well, it's very simple. It's clear that once we divide through by the a e to the RT, and that's perfectly legal because e to the RT can never be 0. And so we won't be dividing by 0. We get r equals negative r of big R over L. Okay, this little r is an unfortunate symbol to use when we have a big R, but that's generally what we use when we do this sort of thing. So we get r equals negative big R over L, and then we substitute that into this form, and we get I equals a e to the negative r over L times 2. Okay, and that's what you would get if you didn't have a source. Now you say, well, why would you do this without a source? Well, maybe what we do is we get some current going in this inductor, and we have a switch, and we've seen that kind of configuration before, kind of a double switch that cuts out the source, so it just bypasses the source, and now we've got a current in the inductor, and of course that same current is going to be running through the resistor. Well, when we cut out the source, doesn't that just stop the current dead? Well, no, it doesn't, because in order for the current to stop, it has to decrease. And if the current decreases, the flux decreases. And if the flux decreases, you get an induced voltage. And in that case, the voltage is around this way, and it gives you a current that goes back the other way. And things happen, and we'll talk about that in more detail, but you should have the idea that if you close this switch, and at the closing of the switch you cut out the source, well, close the switch, get the current going, then cut out the source, have another switch that bypasses the source. So you start with the current going here, the current's going to go for a little while. And it's going to fall off, as you would maybe expect, and it's going to fall off at a rate that's exponential. Okay, you're going to have an exponentially decreasing current. And that's what this gives you. Now, if you close the switch and keep the source there, well, then you've got to find a function for I that matches, that allows this equation to match the voltage of the source. You're still going to have this part of the solution. That goes back to this thing called superposition. But to this, you're going to add some function for I, such that when you plug into that I, you get the EMF of the source. Well, it turns out that very easy I that you can use. Just let I did a little more here, but if you let I equal the EMF of the source divided by R, then this term gives you EMF of the source divided by R. And if the EMF of the source is constant, then the derivative of that I is going to be 0, because I is going to be a constant. And you end up with I equals EMF of the source divided by R. You add that to the AE to the negative R over LT, and we'll do this in more detail. I say that, well, A is going to be, in the case that I said, negative of this, so that I ends up being EMF of the source divided by R times 1 minus E to the negative R over LT. And if you're familiar, as you should be from what we did in lab last time with capacitors, we had a very similar equation for the voltage on a capacitor. You see that your current is going to asymptotically approach the EMF of the source divided by the resistance. So that after a while, the current is going to pretty much be what it would be if the inductor wasn't there, because the more current, well, the more the current increases, the more slowly the current changes and so forth, and I don't want to talk about that right now, go beyond what you can understand at this moment, but if you think about it, that becomes pretty clear. So this solution makes perfect sense. So the formality of the solution, we assume I equals AE to the RT, and we solve this equation just by substituting this in here, and we get the nature of our solution. Now, the EMF of the source and other things are going to determine what A is, the initial conditions and so forth, but that's going to be straightforward. If I tell you the current is 4 amps at T equals 0, then you know that, well, T equals 0 gives you just 1 for the exponential, so that the A is just going to be your initial current. In different situations, you'll have different results. If you add a source EMF, if it's a constant EMF, you get this. Now, if it's not a constant EMF, it's usually going to be a sine wave or maybe a square wave. If it's a sine wave, it's going to be easy to figure out what I has to be. It's got to be some combination of sines and cosines. It's the only way you can take derivatives and add up to a sine and cosine, sine or cosine. If it's a square wave, well, you got to use Laplace transforms, and we haven't even been there in differential equations, so we're not going to talk about the response of a square wave. Or you use Fourier transforms with different types of non-sinusoidal sources. Usually have to do that. Okay, well, that's more than you need to know. What you need to know, again, I equals AE to the RT, plug it in, you get this solution. Very simple. And if you have a constant voltage, then you're just going to get this. And it's not hard to understand why. Now, we're going to talk about an LRC circuit, but the formulas are, the equations are very similar, and the way you solve it is very similar.